streaming to YouTube right now, and all right, so I need a code as expected. All right, it's doing its magic thing right now. I'm just looking at the clock. We got about 5 more seconds to go, and then we'll get started with today's class. All right. And here's the mind map for today. I find this, to be a kind of useful tool for myself. I'm not sure whether you guys use it or not, but for myself, it is a useful tool to kind of remind myself what to need to be done. Oh, right. I forgot to share screen on Discord. I'm gonna have to script all of this at some point in time. All right, there we go. There we go. Thank you. Thank you for reminding me to share screen on Discord. All right, so Discord should be up and running, and YouTube should be up and running as well. So, yeah, I just verified that the YouTube side is up and running. So I'm gonna close that window. All right, so there's a comment here. Can I explain about the borrow part using an example from a lab? Yeah, I can surely use your example. So the overall borrow is basically, the most significant T bit. So that's actually it's explained down here a little bit here, right here. So it's when we perform an n-bit binary subtraction, and all the questions that you have in the lab on Tuesday are 4-bit binary subtractions. So we are basically looking at T of 4 as the overall borrow of a subtraction. So I'm not sure whether that answered the question, overall question. I can do the example in just a little bit. But let me first go over a few items for today. And the first item, I just talked about it, vaccination requirements. So all I want to do is to make sure that you guys are aware that there will be some requirements coming out. There will be some policies, but the district needs to kind of think about, all those, policies first before they make it public. And at this point, I think there are some inconsistencies. So if you are on campus for some of your classes, you might want to refer to your professor to ask about the specific policies regarding vaccination. If you're not taking online classes and you receive a notification from one of your professors about the requirement of vaccination, you might want that professor to help clarify, how does it apply to online classes, people who are only taking online classes. And the professor may actually need to talk to the dean, to get some clarifications, and the dean may need to talk to the supervisor of the dean, and so on and so forth. Because right now, I think there's some inconsistencies of what people know about the policy. So there's that. All right, so I'm going to disclose a few things about today's lab first. So today's lab is about double, okay, which is not a topic that we are going to, well, we may be able to cover some of that, but we may not. But look at this as a primer, okay, for the topic, of double precision floating point numbers. In other words, this is just getting you to understand the concepts involved in double precision floating point numbers, and it is not specifically about floating point number representation. Yes, you can. I'm not sure whether you can still get $200 if you submit your record. I thought the deadline was September 1st, or is it now October 1st? I can probably find the link, but there are some caveats to it. It's October 1st? Woohoo! All right. So I think they only need the first shot too, right? Is that correct, Terrence? They only need you to have a record of the first shot, not both shots, to get the $200. Oh, is it $100 for each shot? Both? Okay. Thank you. Thank you, Dario. Yeah, I really don't know the details because I don't think that applies to me. It only applies to students. I have to enroll in somebody else's class to get eligible for that. Thank you. Thank you, Terrence. That is very helpful. Cool. All right, so getting back to scientific notation. So in scientific notation, if you see negative 1.23 e negative 45, it really is representing the value of negative 1.23 times 10 to the power of negative 45. So the negative 45 is representing the power of 10 that you need to multiply to whatever number that is preceding the lowercase e. So it is important to understand that e is not the natural log constant. So normally when we say, e 1 2, with superscript 1 2, that means, we are raising the natural log constant to the power of 12. Okay, but that is not the case in this particular notation. We are not multiplying negative 1.23 and the natural log to the power of negative 45. That is not what we are doing. Okay, the exponent or the base of the exponent in this case as a scientific notation is 10. Okay, because I have seen people typing, just copying and pasting into a online calculator without thinking about what e is representing. That does not work. Okay, I can guarantee that that does not work. So you have to understand what this e is representing first. And then two general rules, that you can also use. It's not required, okay, but it does help make things easier. You can always use a spreadsheet and use a trial and error method to answer some of the questions. So the first one is just a general log type of equation. If x equals to y to the power of p, then log of x is p times y. Log of x is p times y. So that's one equation. And then the second equation is you can change the base of your log. If you want to find out what is log a of x, you can use log b of x divided by log b of a to find out what is log a of x. Yeah, so generally speaking, this log here is. Oh, you're right. Okay, so let me think. Okay, let me be extra clear. I make a mistake. Let me be correct here. I made a mistake here because p times the log of y is what we need. There we go. That makes sense, right? So no matter what base you use, this equation still applies. So if x equals to y to the power of p, then log of x is the same as p times the log of y. But these two log must use exactly the same base. So you cannot use log 10 for this one and log of e for this one. They must use the same base. And as long as they use the same base, everything should be okay. No, you did not misread. I mistyped. I just fixed the y to be log of y. So these two equations, may be useful. Okay, if you already know how to use log, this is just a reminder. If you do not know how to use log, then we have a little bit bigger of a problem because that concept is really, really important, for this particular lab. All right, so there's that, and what we'll spend the rest of today doing would be looking at comparison. And I'm going to go back to Daria's original question with a particular example, and I'll give you even more examples than that, okay? Because I think in this case, having plenty of example can be helpful to understand why they are useful. Now, the definition is not really that dependent on examples. Okay, so let me just magnify a little bit more so we can see the equations better. The B flag is really just T of n. Now n is referring to the width of the binary subtraction. So once you are done with a binary subtraction, the B flag is basically T of n. So if you look up the T row, it is the most significant bit of the T row, which is for bit n. And the meaning of the B flag is it is a 1 if and only if the minuend is less than the subtrahend unsigned. Using our terminology, the minuend is x and then the subtrahend is y. The S flag is also very easy to define. It is the most significant bit of the difference. So it is d subscript n minus 1 because n minus 1 is the most significant bit of the difference because we count from 0. So what does it mean? Well, it is a little bit more complicated in this case. The S flag is a 1 if and only if the minnow n is less than the subtrahend signed, but it only works if there's no overflow. So we're going to have to talk about what is overflow. This is how overflow is defined. And this time I use the ampersand, ampersand, and the bar, to indicate conjunction and disjunction, because there seemed to be a confusion, of are we multiplying? Is this a multi-bit thing, or are we using conjunction in the when I did not use ampersand, ampersand? Now the context of the O flag is it is a single bit. It is a Boolean value. So as a result, the context tells us that xn minus 1, yn not yn minus 1. That is basically a conjunction because we want to arrive to a single Boolean value. So when we have that context, then it is basically just a conjunction on this side, conjunction on the other side. Each conjunction gives us a Boolean value. Then we can use a OR to combine the two Boolean value into the actual O flag. So the O flag, what is the meaning of the O flag? The semantics of the O flag is it is a 1 if and only if the difference cannot be stored in n bits. Okay, so I'll give you an example of what that means. And then we have the L flag. The L flag, mechanically speaking, the lab is for the most part, and actually for the whole part, mechanical. In other words, we just have to find out how to perform the bitwise operations. But the meaning is not really talked about much in the lab. So the meaning of the L flag is it is a 1 if and only if the minuend is less than the subtrahend signed. So it is quote unquote an improved version of the sign flag. Okay, because the sign flag is okay to use if and only if there's no overflow. Because when there's an overflow, the S flag will be opposite to what it is supposed to be. The L flag, on the other hand, takes care of that because it is combining the S flag and the overflow flag using exclusive OR. So this is kind of what we'll be focusing on today, from now all the way to the end of the lecture. If we have time left, we can move into double precision floating point numbers just a little bit. If not, then I'm pretty sure we can finish all of these topics today. All right, so I got a few people typing in the text channel. I'm going to wait a little bit and I will start up my tablet and do the screen share, because what we'll be talking about today is going to be something that will be easier to visualize when I use the tablet. All right, so we got the L flag has a formal name of less than. So that's one way to look at it, is it is just less than. LOL can be one of those two. You can look at the L flag as LOL flag. That's your choice. I mean, we get to choose, how we want to look at the L flag. What is the symbol in the L flag? We have seen this already in the past. It is exclusive OR. All right, so I am getting into the notes for this class, and it is up and running. All right, so we are going to take care of the example that Daria had quoted, at the beginning of the class. So we'll start with that one, and I need to check to see if this is inside the recorded window. Move it down just a little bit. That's all good. All right, and let me go back to the text channel to make sure that I am not missing the sample that I'm supposed to go through. Okay, it's 0, 1, 0, 0 minus 0, 0, 1, 0. All right. Okay, so we'll start with that. All right, so there we go. So we got 0, 1, 0, 0, and we are subtracting 0, 0, 1, 0 from it. And I'm not going to use base 2 for every single thing now because they're all base 2. Okay, so unless it is not base 2, I will just we'll just assume all of these are in base 2. So this is x, this is y, this is q, this is t, and this is d for difference. So we can work this out, column by column. We can work this out, row by row. So I'm going to work this out, row by row first, because the Q row is really easy to figure out because the Q row is the exclusive OR between the X and the Y. So 0, 1, 1, 0 over here. Now the T row is a little bit trickier. So if you were to apply the borrow look ahead mechanism, yes, you can actually figure out the entire T row without using the propagation technique. But the T3 and T4, when you use the borrow look ahead equation, is actually quite complex, and we human beings can only work sequentially when it comes to doing this kind of math. So using the borrow look ahead technique does not help us. Okay, it does help the computer because the transistors can all operate independently and in parallel. But when we are using our conscious mind to work on something, we are for the most part completely sequential. So it's not going to help us. Alright, so we're going to do it sequentially. T0 is assumed to be 0 because we are not chaining a bunch of subtractions. And then we have this has no borrow, this has no borrow, so the overall borrow from bit 1 is going to be a 0. And this is going to be 0, this is going to be a 1. Now we have 0 minus 1 being a 1 with a borrow of 1. And now we have 1 minus 0 being 1. 1 minus 1 is a 0. Neither of these subtractions is going to need a borrow from digit 3. So we have a 0 on this side, and then we have 0 minus 0, which is a 0, 0 minus 0, which is also a 0. But remember, the overall borrow is T4. This is T3 right here. So we need, we need to figure out T4, which is funny in a way because T4 is also the name of a shop that sells boba and other kinds of drinks. I know because I sometimes drive my son to that place so that he could meet up with his friends. So T4 is going to be a 0 in this case because x3 minus y3 does not have a borrow of 1. Q3 minus T3 also does not have a borrow of 1, and as a result, T4 is a 0. So we got a few people typing. I am going to try to answer those questions before proceeding. I really like this new way of using the tablet. Before it has to be tethered by USB. Now it's wireless, so I can actually use the tablet anywhere without having to be tied down to the length or the reach of my USB cable. All right. Yep. So Daria said basically T0 is no, it's not always going to be 0. It is going to be 0 unless we are chaining, as Jonathan typed right above. If we're chaining, it is not going to be a 0. And in the test, there's no assumption that T0 is going to be a 0. So the sample test that you got the other day has no such assumption that T0 is always going to be 0. You have to figure out T0 just like the rest of the bits. And Jason is still typing. Oh, there we go. I am sorry, could you explain how you got 1 in bit T2 again? Alright, so I think to answer that question, I am not going to be direct. And you guys already know that I am not really likely to answer a question like right away, straight away. So I would refer Jason and anyone who has a similar question to review binary subtraction. And to be more specific, there is an equation that talks about how to find t of I plus 1. So now you have to remember how t of I plus 1 is defined. It makes use of certain things, so we know it makes use of I, xi, yi. It's going to make use of qi, ki. And the rest, I'm going to leave it up to you guys to figure out. All right, so Daniel has a comment. T4 is 0 because it doesn't have that much about it's not about the single digit difference, which is the Q and the D. It really has to do with the B function. So I'm gonna have to have you guys to look up what is the B function. B of xy is what? How is it used? How is it defined? How is it used? That is because all of this is the stuff that we have already talked about. It doesn't make sense for me to repeat a previous lecture today, because otherwise we won't be able to finish all the material that I'm supposed to finish for this class, which also means by the time you transfer to a 4-year university, which assumes that you already know everything that I'm supposed to teach in this class, you won't have everything that you're supposed to know. That would not be good for anyone. So I would advise you guys to look this up, find out what is the definition of T subscript I plus 1 in terms of, okay, it depends on xi, yi, it depends on qi, ki, but how? Also, look up what is b of xy in a binary subtraction. Okay, specifically when we apply b of x, bxy to a binary number subtraction, how is it defined? Let's see. Oh, okay. I'm not really sure, Terrence. I'm not really sure whether you guys are ready for more depression. But since you asked, I'm going to tell you. Not yet. Okay. Well, how you look at this is up to you. Okay. If some people want to look at it as a source of depression, that's one way. But on the other hand, if some people just want to look at it as a data point, that's the other way. So the lame thing is we go into new lectures still not having mastery of the previous stuff because questions are asked and you refer to us to other sources to learn rather than learning it from you. Okay. I can see that is how Matty looks at the class and how I teach the class. I definitely respect, her opinion. But from day one, I already gave you guys the success mind map. The success mind map outlines the resources that are available. Now, I don't really mind clarifying concepts when people say, from your notes, I can interpret it in 2 different ways, 3 different ways, and I'm not really sure which way you mean by that. Okay, I can clarify, not a problem. But not knowing how T of I plus 1 is defined is not a clarification question. Not knowing how bxy is defined is not a clarification problem. It's not a clarification question. So those are different compared to I'm not really sure. I know how this is defined. I know how that is defined, but I'm not really sure how they are connected. That is not so that question I can answer because it's about connecting, and different people read things differently and they connect in a different way. And sometimes certain things that click with some people does not click for other people. So I can kind of understand that and further explain that. Yes, well, it's kind of like a reference. So I would refer to things that we have already talked about. And remember, you are supposed to spend 13 hours a week for this class. So there's that too. I really don't know how much time anyone spend in this class, and it's not a strict requirement. There's no necessity to spend 13 hours if someone needs less time to absorb all the material. Okay, but 13 hours is a suggested amount of time for this class. So if somebody is only spending like 3 hours, I would say, well, I don't think that's enough time to really get all the content and all the material that's necessary for this class. All right, so Daniel is correct. B of xy is not xy. So the question is, how is it related to this? So, all right, so Daniel, I want you to find what is T of I plus 1. That would be the next thing to chase down, because t of I plus 1 is okay. I'm gonna give you guys a big clue here. T of I plus 1 makes use of the b function. So that is the next thing to chase down and try to figure out how everything is connected. All right, so getting back to the data point, when I took assembly language programming, and this is from San Francisco State University, which was not particularly a well-known university for computer science. It's good for, I think, two things. I think business administration and nursing was at the time, the two strong areas of San Francisco State University. So computer science was kind of like, yeah, we have those two, that kind of major. When I took CISP, or what is equivalent to CISP310, the class started off with 60 students. So it filled up the whole lecture hall, and it was in the format of once a week kind of format. So we met only on Mondays from 7 to 10 p.m. So it's a 3-hour time slot, and the lab is not even attended by the professor. Okay, so there was a lab, but it wasn't even, the professor was not required, during the lab time. All right, so by the time we got to the end of the semester, there were less than 15 students left in the class. And that was in, I think, 1986. So in 1986, that was my experience with taking a class in assembly language programming. Now, that is not a predictor, okay? I am not trying to recreate the attrition rate of that class. No, by no means am I implying that I think that was okay, but I am implying that assembly language programming is basically a difficult class. I mean, for most people, it can be a difficult class. Jonathan has to ask. I enjoyed every moment of that class, but I was told that I was not typical. So, don't take it as a general thing that can apply to most people. All right. Oh, their CS program is much better now. Much better in the sense of they have expanded. There was one time when the entire College of Engineering of San Francisco State University was about to be next. They were about to be cut off from, they were about to drop the entire College of Engineering. That was no longer the case. All right. So let's get back to, what the topic is on hand right now. All right. So all I can see in the text channel is still the bxy equals to not x and y. But where's the context? Where was the b function used? I described that in lecture. I gave you guys a C definition of the b function and a definition of the r function for any base comparison. And I gave you a relationship between the b function and how it is utilized for the borrow bits for the t's, and I also gave you an example in base 10 of how the t is computed. So the annual type is okay. So what the annual type in the text channel is correct, and the plus can be an addition. That's before we discovered that we could have used a or instead of an addition. So in the general sense, the plus can be an addition because we also proved that the two b functions, when we define t of I plus 1, cannot be true at the same time. That we also talked about in class. So in the proof, that not both b can be ones at the same time. In that proof, if people need clarification of I'm not really sure how this links to the next step, I'll be happy to explain that. Okay, but it is already explained, so I can only fill in the gaps in the previous explanation. All right. Okay, I understand that. That if one person is complaining, there are 10 more people who might have the same problem. But the question is it a problem about my explanation, or is it a problem of maybe people are not understanding the material because either one, they may not have been spending enough time to read the material, or two, they are reading the material, they're spending enough time, but they are not making the connection. So just because a whole bunch of people have exactly the same problem does not make it a problem that requires a particular treatment. Okay, so solving examples help a lot. Let's focus on that. Okay, so let's focus on that, and we'll use more examples in base 2. So thank you, Daria. This is a great way to move ahead, because now we also want to find out what is B, what is S, what is O, and what is L for each example that we're going to go through. So in this case, what is B? B is T of 4, which in this case is this particular 0. So I'll even make a picture of what 0 we are talking about. What about the sign flag? The sign flag is the most significant bit of the difference. The difference is the last row, and this is the most significant bit of the last row. So I'm going to write here, this is MSB of D. And you note how the B is in lowercase. That's because uppercase means byte, lowercase b means bit. And in this case, we are referring to the most significant bit instead of most significant byte of D, which is also known as D subscript 3 in this case. And it is a 0. And this one is referring to this particular 0 here. What about overflow? Okay, so if we look at the definition of overflow, it is x of x3 not y3 and not d3, or not x3 and y3 and d3. So we just have to plug in the numbers, right? So we have 0 and not 0 and not 0, or not 0 and 0 and 0, which is 0 or 0, which is 0. Y3. Okay, so when people ask questions like Y3, you have to tell me the context, because we have a bunch of 3's in the equations. Which 3 are we talking about, or are we talking about all of the 3's? And Ashton is correct. They are referring to the most significant bits. Most significant bits. Okay, so because we count the bits from 0, right? This is bit 0, bit 1, bit 2, this is bit 3. So in a 4-bit binary subtraction, bit 3 is the most significant bit for x, y, q, and d. T is different because we need one more bit for the borrow bits, for the t bits, to indicate the overall borrow. I don't want to use the term last bit. We only talk about the most significant bit. The most significant bit is the leftmost bit. All right. Yes, the least significant bit is bit 0, at least in this case, because we don't have decimal points and places to the right hand side of a decimal point. So bit 0 is going to be the least significant bit, and then the leftmost bit is going to be the most significant bit. There we go. All right. Any other questions before we get to the L flag? Any clarification that is needed? So Ryan is typing something. All right, so the question is when T4 is a 1, why that doesn't get brought down into D? That is correct because D needs to have exactly the same width as X and Y. So the only reason why T has one extra bit, which is T4 in this case, is because we need to understand what is the overall borrow after the entire subtraction. That's the reason why T has one extra bit. All right, so Brian is still typing something, but I'm going to go ahead and talk about the O versus the L flag and also the sign flag. So this is the exclusive OR between the sign and the overflow flag. The sign flag is 0. The overflow flag is also a 0. So we have 0 exclusive OR with 0, which is, well, what is it? What is 0 exclusive OR with 0? That's right. Okay, so the L flag is a 0. All right, cool. So mechanically, now we have figured out every single bit. The question is, what does each one mean? Okay, so that is actually what I would think is the main purpose of today's class, is to add semantics to the mechanical Boolean expressions that we have been using to extract the bits. Okay, so the most important bits, well, all four are important. Okay, so we'll start with B. So we say B is a 1 if and only if X is less than Y unsigned. Well, that actually makes a lot of sense, okay? Because if you think about T4, what does it mean? What does it mean when T4 is a 1? Well, when T4 is a 1, all that really says is, okay, we have a borrow either from the subtraction of x3 and y3, or we have a borrow from q3 minus t3. So when it is, if it is because of x and y, because x is a 0, x3 is a 0, y3 is a 1, then it is pretty clear in that case that the unsigned value represented by x is less than the unsigned value represented by y. Integer value unsigned integers only need to pay attention to b. SOL are not applicable to unsigned interpretation. Okay. So here's the next question, okay? Because someone may say, but that's not the only reason why T of 4 can be a 1, because T of 4 can be a 1 when we subtract T3 from Q3. Well, the only reason why Q3 minus T3 can have a borrow is Q3 being a 0 and T3 being a 1. So now the question is, what if T3 itself is a 1 and everything else, all of these are zeros? Well, that's because of an earlier reason, right? So either x2 is less than y2, or x2, y2 are the same, but q2, which is guaranteed to be a 0 in that scenario, is a 0, and then t2 is a 1. So we extend that reason back to another column, and then we can extend it back to one more column, all the way from left to right. So the idea is b equals to 1 overall speaking, is because the unsigned value represented by x is less than the unsigned value represented by y. All right, so we got a few questions here. Justin says T4 equals to 1 equal, oh, that's a ternary operator. Oh, that's a joke. Yes. No, that's cool. I like that. You can be the marketing person for T4. Offer them this particular slogan. Daniel says this example would be great to watch back later when stuck. I would agree. Okay, for certain people, I mean, it doesn't apply to everybody, but I think it is always a good idea to time mark the whole thing. And I totally forgot to take roll, so I'm going to take roll now. And I need to change the time because my alarm clock had gone off already during an earlier conversation. So let me change that first, and then I'll go ahead and take roll. So my suggestion is for you guys to kind of keep track of how much time you spend for this class. I'm not really saying that you have to spend exactly 13 hours a week. That is just not, possible, okay? But it is important to kind of track how much time you're spending, because if you're spending like 5 hours a week for this class, that may not be enough time. Okay, because without knowing it, there's just no way to even know whether we are spending enough time or not. So, all right, so let me see. Let me refresh. If you refresh your screen, you will see the row taking activity for today, and the word is overflow. I'm going to type it here, overflow, lowercase. All right, so I already said on Tuesday that next Tuesday is going to be our practice exam, and the actual exam is going to be 1 week after the practice exam. So that will put the first exam to be 12 days from today. Today is the 16th plus 12, so that will be the 28th. So September 28th is going to be our first exam. Now, I chose the word overflow before the boba joke, because otherwise I would have used boba, which I personally do not like in my drinks. All right. And by the way, boba is can also be a hexadecimal number. B0BA, can actually be a bit pattern. It can specify a bit pattern. Exam 1 is a midterm that is specified in the syllabus. Yes, I'm giving you guys another pointer. Yes, that is the approach that I do in my classes. I give you pointers. Let's pass by reference when it is possible instead of passing by value. All right, so let me check and see how many people have done the row taking activity, and then we're going to move on. I haven't seen anyone complaining that it is not released, because sometimes I get the time wrong and people go like, oh, well, hold on a second, I cannot do it. All right, so most people have done it. All right, so let's go ahead. You don't pass by value, wouldn't want us to change the values on you and move the exam. No, I wouldn't have any idea how you have changed something if it is passed by value, because if you pass a parameter by value, the subroutine can change it all it wants, but the caller would not even know that it has changed. I'm giving you a copy of something, and you can do whatever you want with it. I'm not giving you the original. Yep. Is it going to be midterm? I'm not really sure. It is an exam. It takes up 20% of your final grade. So you can call it an exam. You can call it just exam 1. You can call it, however, assessment number 1, 1/3 through the semester. It doesn't really matter how we call it. It is 20% of your grade. And it is going to have the lecture time. So in 12 days, we are going to use the lecture period for the exam. Yeah, we can go over the practice exam, but I want to finish what I need to talk about today first. Which day will it be? It will be the September 28th. I believe that's what it said. It's not going to be next Tuesday, it's going to be the Tuesday after next Tuesday. It is 12 days from today, which is the 28th of September. We are not going to have a lab on that day, because some people may need more time because of DSPS accommodations. All right. Well, there's no need to have a crying face, because it's still like 12 days away. So we just need to go through the practice exam, the practice question. Once we are done with the discussion today, we'll go over the practice exam and figure out how to solve those problems. And everything is really kind of mechanical. Okay, for this class, a lot of stuff is very, very mechanical, but you do need to keep an inventory of all the definitions. And if you have all the definitions in one spot, it'll be easier to see the relationships between the definitions, because they are now right next to each other. So you can see how t of I plus 1 relate to b, and how it relies on the x, y, q, and t to do the calculation, and you can figure out how q is defined using r, and so on. So having all the definitions in one spot is going to be helpful. All right. No, there's no lab. I'm not really sure what you mean by lab kind of stuff. I'll give you, basically in the exam, I give you a Google Doc, and you write your answer in the Google Doc, and at a certain time the Google Doc will be unshared, and I'll use that for grading purposes. So, it's not going to be on Canvas. All right, so let's get back to our topic and continue to use more examples to explain the concepts. All right, so I gave you one example here. So I'm going to give you another example where the B flag is going to be set. Okay. So in order for the B flag to be set, we need x to be less than y using the unsigned interpretation. So I'll give you one example just like that. So we're going to use, let's use a fairly extreme example here. So 0, 0, 0, 0 minus 1, 0, 0, 0. Okay, this is the binary subtraction. So when we are performing the binary subtraction, there's no need to say, okay, but hold on, Tech, are we looking at these bits as unsigned or signed? We don't need to worry about that, okay? Because signed or not, we are going to use exactly the same mechanism to perform the binary subtraction. Okay, so this is really important, because you just don't worry about signedness when you're performing the subtraction. It is the interpretation of the zeros and ones after the subtraction that is important when we say, but hold on a second, these are signed numbers or these are unsigned numbers. The way we interpret the zeros and ones afterwards is what differentiates signed versus unsigned. All right. So that's one way to look at it. Okay, that's one way to look at this subtraction. You can say it is 0 minus 8, but there's an alternative way to look at the 1, 0, 0, 0, which I'm not going to say right now because I'm going to talk about that later. Okay, so the Q row is going to be 0, 0, 0, 1, because 0 exclusive or with 1 is 1. The T row, in this case, we start with a 0 here. Now remember, in the exam, you cannot assume T0 to be 0, okay? But in this case, because this is not a question of that format, and we are not carrying on a chained subtraction, so T0 is 0 in this case. And 0 minus 0 does not have a borrow of 1. 0 minus 0 does not have a borrow of 1. This is going to be 0. Likewise. But this one is going to be a 1 because 0 minus 1 has a borrow of 1. So that's a 1 over here. Justin, the answer is no. It is not. It has nothing to do with mercy. It really has to do with, it really should not make a difference. It really should not make a difference in terms of what logic you are going to need in order to figure out what T0 is supposed to be. All right, so we'll address the Perry's question. So let me finish this first. Okay, so this is the D row is really just the exclusive OR between the T and the Q. So 0, 0, 0. We got a 1 over here. All right. Chained subtraction, it means that you have a certain width of a subtractor, but you want to carry on a subtraction that has a wider width. Okay, well, that's bad. English there, but let's say you have a 4-bit subtractor, but you want to work with 8-bit numbers. So that means you have to break up the subtraction into 2 chunks. So you perform the least significant subtraction first. So the overall borrow of the least significant 4-bit subtraction becomes the T0 of the becomes the T0 of the 4-bit subtraction of the more significant part of the 8-bit numbers. Whew, okay, that's a mouthful. That is what it means to be chained. But we are not going to talk about chained or not, okay, in this class, not yet, okay, because today I just really want to focus on BSOL, okay. All right, okay, sure, absolutely, absolutely. Okay, so now we're going to look at this and figure out what BSOL should be. So B is 1, okay? And I'm not going to do the full explanation as before because that portion is the same. So I just want to focus on the exact value in this particular instance. S is a 1 because this is the 1 that we are talking about. O is 1 in this case. So I know it's because, okay, so there's an easy way to tell whether you have an overflow of 1 after subtraction. If x is different from both y and d, you have overflow. That's it, okay? So if you observe 0, 1, 1, you have an overflow. On the other hand, if you observe 1, 0, 0, you also have an overflow. So that's really just a very easy way to look at the original, expression here, and it just translates to y and d have to be the same, and they are both different from x. That's all it's saying. All right, so now we look at the L flag, and L flag is the exclusive OR between the S and the O, and in this case we have one exclusive OR with 1, which is a 0. Now we are going to take a little bit of time to really understand what does it mean, okay? What does it mean? So unsigned interpretation is easy, okay? Because when we talked about base conversion, that is unsigned interpretation. So I'm not really sure how many people still remember base conversion. Base conversion means, we look at every single digit and we say each digit of a number is representing the quantity of the base to the power corresponding to that position, and that's part of a sum to get to the actual value being represented by the number. Okay? Any questions about that part? All right. So if there's no question about that particular statement, where can things be negative when we are doing base conversion? In other words, when we are adding the each digit multiplied by a base to the raised to the power of the position of the digit, they're all non-negative numbers. I cannot say they're all positive because 0 is neither positive nor negative. So, but I cannot say there's nothing there can be negative. And that's why, that's basically the unsigned interpretation of a base 2 number. So unsigned interpretation has been done since we talked about base conversion. What about the signed interpretation? So the signed interpretation is the one where we have that number wheel thing. Okay, now we haven't really talked about the number wheel thing, so now is a good time to talk about the number wheel thing. So I'm going to draw a wheel here, circle, and I'm going to break it up into the number of slots that is equivalent to how many unique bit patterns, zeros and ones, you can have when you have 4 bits. So can someone tell me, if I give you 4 bits, okay, how many combinations of zeros and ones can I get? How many unique combination sequences of zeros and ones can I get? 16 is correct. 16. 2 to the power of 4 is 16, not 8. Yes. Okay, very good. 16. So I'm going to give you 16 slots in this wheel. Okay. There we go. And each slot is representing a particular bit pattern. So we're going to start with 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, and finally 1, 1, 1, 1. Okay? So why is it real? Because when you take a math class, okay, they talk about numbers and they say number line, okay, it extends to infinity on both sides when you're talking about integers. Well, in computer science, we don't have an infinite number of digits. Okay, whenever you declare a variable in C or C++, you are limiting to a certain width. Depending on the architecture, okay, if you're using a 64-bit architecture, then int is going to be 64-bit wide. If you're using a 32-bit architecture, int is going to be 32-bit wide. Then in that case, a short is going to be 16-bit wide, but you can also use char as 8-bit wide, and so on. The point is, there's a certain width limit. In other words, everything is modular 2 to the power of the width of your integer. Okay, you don't get to have an infinite number of digits when it comes to the integer type in most programming languages. So that means eventually you're going to come full circle back to 0. So in this case, we have a kind of really watered down version compared to a real integer type. In this case, we only have a width of 4 bits. And as a result, we have 16 slots. Okay. And if we were to assign values, unsigned values to each one, it's not that difficult, right? So we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. That's pretty easy. Now, when you're working with a program, most programs do not really need negative numbers, by the way. But there are certain programs that need to represent negative numbers, particularly if you want to see if it is time to do a certain thing. You take the time mark or the timestamp, before, and then you compare the timestamp with the current time, and then you compare that to a particular value for the timeout. So depending on how you work the math, okay, you might need signed representation, because you might need to tell whether it is before the timeout or after the timeout. Now, as I said, it depends on how you set up the comparison, because in a certain way you can use just unsigned values for that purpose. But so the bottom line is there are situations where we need to represent negative values. So now the question is, how are we going to represent negative values? Well, I think some of you probably remember that we have such a concept called 2's complement, which is the negation of something, right? That's something that we talked about, I think, the previous class, I think. So let's take a look at 2's complement. Okay? No, that is not bitwise negation. So 2's complement of a particular bit pattern is defined to be 1's complement of the same bit pattern plus 1. That is something that we talked about in the previous class. So this is what I'm talking about is I need people to review the content of a previous class. Okay, because I cannot now go back and re-explain the whole thing about 2's complement. That is just not going to be a good use of time in this class. And we also claim that 2's complement is doing the same thing as arithmetic negation. That is also established because when we are working with modular math, okay, in particular because we're using base 2, so this is modular, okay, percent 2 to the power of n being the width of our integer. Okay, so how is this going to apply in the question that we have? In other words, how do we represent negative values? Okay, let's take a look at let's pick negative 3, okay? So we want to see how negative 3 is represented. But Two's complement only works with binary numbers. -3 is a value. The way it is written here is a base 10 representation of the value of -3. So I can easily rewrite this and go like, oh, okay, fine. It is the same thing as the arithmetic negation of the binary version of 3. The binary version of 3 using 4 bits is 0, 0, 1, 1. Okay, this time I put a subscript of 2 just to emphasize that this is in base 2. Are we still doing okay so far? Because all I did here is to change 3 from base 10 to base 2. Okay? Now I'm going to look at this and go like, hey, this is a binary number, and with any binary number, we can use 2's complement to perform the arithmetic negation. That equality or that congruency was established in the previous class. So now we say, okay, it is congruent to 2's complement of x, which is 0, 0, 1, 1 in base 2. And we know that, so this time it is a equal to C1 of 0, 0, 1, 1 in base 2 plus 1. Okay? And C1 is 1's complement, which is otherwise known as bitwise NOT. So bitwise NOT is just flipping all the zeros to ones and all the ones to zeros in place. So we have 1, 1, 0, 0 in base 2 plus 1, and that turns out to be just 1, 1, 0, 1 in base 2. So when you look at the entire chain, this is saying -3 as a value is congruent to 1, 1, 0, 1 in base 2. Oh, that is really kind of suspicious. I can swear that there was a number already assigned to that slot. So getting back to the number wheel, we can see that 1101 is already taken up by the number 13. So now we're going to say, well, guess what? This is also -3. So -4 goes here, -5 goes here, -6 goes here, -7 goes here, and -8 goes here, -1 goes here, and this is where -2 is. All right, and this adds I think it certainly adds a lot of confusion, right? It's like, so which one is 1101? Is 1101 -3 or is it 13? So my answer to that particular question is even more confusing. I'm going to ask, why do you care? Why do you care? Because it doesn't really matter, because the binary subtraction mechanism works out in both ways. Okay, so you might say it doesn't seem to work out in this case, which you're correct. Okay, but it does work out in many cases. So I'm going to show you a case where it does work out in both cases, and then we're going to get back to this one where it doesn't work out, and it will explain why it is not working out, and also why the overflow flag is important in this case. So let's go ahead and use a new example where it does work out in both cases. So we're going to say, oh, okay, I get it. So let's use 1, 1, 1, 1 minus 0, 0, 0, 1. Okay, that should be a fairly easy subtraction. No, there's no quantum mechanics involved here. I wish. I wish, first of all, that I know more about quantum computing, and two, I wish I could teach a class after I get to know quantum computing to teach a class on quantum computing, because I think that's the future. I mean, your generation, now I'm making a broad assumption here that you are somewhere in your 20s, okay, which does not apply to the entire class, obviously. But I think if you're in your 20s, in your career as a computer science person, computer programming, developer, and whatnot, in your lifetime, you will get to see quantum computing. So, I think that's going to be an interesting thing to get into, but I cannot talk about that yet. Okay, so now we have this here. So this is a pretty easy one because there are no borrows whatsoever, right? So 1 minus 1 is a 0, 0. Oops. Okay, I take it back. 0, 1, 1, 1. This is assumed 0 in this case. So 1 minus 1, 0 minus 0, neither has a borrow of 1. 1 minus 1, 1 minus 0, 1 minus 0. No borrow here. So it's going to be the same way throughout the entire thing. So this is the result of the binary subtraction. I do not know, Ian. I'm assuming I'm the oldest person, of this entire collective here, but I may not be the case. Okay, it may not be the case. It doesn't really matter. Anyone with enough curiosity can continue to learn in their entire lifetime. All right, so getting back to this thing here. So, okay, so Colton has written here, so for 2's complement, the highest value that can be calculated is the highest value of a signed x bit component in base 2. I'll get back to that, okay? Because what Colton's question is asking really ultimately connects to the concept of overflowing and also why the overflow flag is important. So we'll get to that. We will get to that. So anyway, let's get back to what you see here on the screen, which is the mechanical aspect of binary subtraction. In other words, I have no idea what 1111 is representing. I have no idea what 0001 is representing. For all I know, it can be pixels on the screen. It can be dots, on the print on the piece of paper that the printer is supposed to print on. So I'm just saying, hey, here's a bit pattern. Here's another bit pattern. We perform what we know as binary subtraction to end up with the corresponding x, y, and d. Okay, that's the whole thing. Okay, it's extremely mechanical. There's nothing to interpret when you just look at the zeros and ones. So now we are also going to mechanically determine what is BSOL. Okay, so B in this case is a 0, S in this case is a 1, O in this case is a 0, and an L in this case is a 1. Alright, so why is it the case? I'm just going to go through this, but this time rather quickly because we have already talked about this, in the previous 2 examples. B is T4, which is this 0 over here. S is D3, which is this 1 over here. O is a 0 because Y and D are different to begin with. So we know that overflow has to be a 0 because in order for overflow to be a 1, we need Y and D, the most significant bits thereof. Okay, we need the most significant bits of Y and D to be the same, and that one bit to be different from X, the most significant bit of X. In this case, you can see that Y and D have different most significant bits, which will make overflow to be a 0 in this case. L is the exclusive OR between the sign and the overflow, so exclusive OR between 1 and 0 is a 1 in this case. The full equation of the overflow is right here. So I can do it one more time, but in general, I think it is best to, okay, it's not, why is it not pasting? Oh, it didn't grab the entire thing, that's why. Alrighty. Alright, so I can just go work it. So overflow is not X, the most, so we're only referring to the most significant bits. I don't think so. So X is, so not 1 and the 0 here and the 1 over here, the whole thing, or 1 non-negated and the negated Y and the negated D That is the expanded version of overflow in this case. So we have 1, 0, 1, which does not fit the pattern of 1, 0, 0, nor does it fit the pattern of 0, 1, 1. But if you work out the math here, we have 1, 0 in this conjunction, so that turns this entire conjunction to be a 0. And on the other side, we have this as a 0 here. This is a 0. So that basically turns this entire side to a 0. 0 or 0 is a 0. So does that work out? Can I do the arrows at the very end, showing where each digit in the equation comes from? Okay. So I think this boils down to a notation thing. That is, I think it's a notation thing because it's really just coming from X, Y, and D, and the positioning of those bits is consistent with the position of these bits over here. Although the negation part, I think I swapped the two conjunctions, but it's still the first one is X, second one is coming from Y, and the third one is coming from D. Yes, so Vlad is correct. X, Y, D. All right, so now we're going to look at this and go like, that looks awfully odd. Since Y and D are different, it'll be 0. Yes, that's kind of what I said earlier. Because we need Y and D to be the same and both to be different from X in order for the overflow to be a 1. Alright, so we are looking at this and show that this is an example where it makes sense both in the signed perspective and also in the unsigned perspective. Okay, so we're going to look at 1, 1, 1, 1 and say there are two ways to look at 1, 1, 1, 1. If you look at the number wheel, you look at 1, 1, 1, 1 can be 15. It can also be negative 1. But when you look at 0, 0, 0, 1, it can only be 1 in this case. So now we get back to this slide and go like, okay, so if we are looking at 15 minus 1, what are we getting? If we are looking at 0, 1 minus 1, what should we be getting? Okay. Yes, Colton, you're correct. 1's complement is bitwise not of X, which is also known as the tilde operator in C. Alright, so getting back to this, okay, so we would expect 14 in this case, and we would expect negative 2 in this case. So now we look up what is the representation of 14. So the representation of 14 is 1, 1, 1, 0. And did we get that? Yes, we did get 1, 1, 1, 0. So that works out, right? So now we want to look at negative 1 minus 1, which is supposed to be negative 2. And now we want to look up the representation of negative 2. So negative 2 is right here. It is also using 1, 1, 1, 0 as its representation. So this is why earlier I said it is okay not to care about signedness when we perform the subtraction, because the subtraction mechanism itself is going to work on both. Okay? So the next question is, how do we tell whether a number is negative or not? So when we go look at the number circle, do you see a pattern? All the bit patterns that has a quote-unquote interpretation of a negative value, what is common to all of those particular bit patterns? So look at the number wheel, look at everything that can be interpreted as a negative number, is that 1 is the most significant bit. So Ashton is right, Matt is right, correct. Okay, so the most significant bit, which is also known as the leftmost bit, which is also known as, guess what, the sign bit of a number, they're all 1s. So this is the pattern that we see, and this is why the most significant bit of a bit pattern is known as the sign bit of that particular bit pattern. Okay, so um, so when you read the notes for the signed versus unsigned no, when you read the notes for comparison, okay, there's an equation. Okay, so there's an equation given a particular bit pattern. It goes I goes from 0 to n minus 2, and then b is the bit of a particular binary number. So it is b of I times 2 to the power of I, and the whole thing is going to be okay, so this portion cannot be negative, but then we are subtracting b of n minus 1 times 2 to the power of n minus 1. This is the value of signed interpretation, and this is straight out of the notes, straight out of the module, which you're supposed to have spent part of your 13 hours per week to read before the class. Okay, so does it work out? Okay, so we're going to plug in some value into this equation here and see if it works out, because remember, examples are useful, right? So we want to look at n being 4, because all the examples up to this point are 4-bit numbers, so n equals to 4. So we want to look at 1110, okay, which is a bit pattern that came straight out of the previous page of this notes here. So when you use this particular expression, the value that you're going to come up with is going to be 0 plus 2 plus 4, and then the whole thing minus 8. And that turns out to be negative 2. So I want you guys to look at this particular example and understand why 1110 as a base 2 number using this particular expression will end up with a value of negative 2. So if you have a question about what is being displayed, that now would be a good time to ask. Okay, so wouldn't those be in the opposite order? Well, there's no order to speak of, because this one is just b0 times 2 to the power of 0. This one here is b1 times 2 to the power of 1. This one is b2 times 2 to the power of 2. And this one is b3 times 2 to the power of 3. But this one is outside of the summation, outside of the sigma, because n minus 1 is 3, and that is not a part of the sigma. So Jonathan is correct. If you want to write out the entire thing, that is why we end up with this sum over here. We got Matt and Colton typing. Alright, so Colton asks, how would we go about declaring a signed versus unsigned bit in something like Logisim? Well, the answer is you don't. There's no signed bit whatsoever in Logisim. Logisim only wants to know, okay, is this a bit? What is the width of this thing? It just has zeros and ones. The interpretation of the zeros and ones is outside of what Logisim can do. And then we have Matt, saying, I mean to match the bits above. Oh, okay, yeah, you can. I mean, addition is commutative, so you can just exchange the order any way it makes sense to you. The way I do this is because I want to do the sigma first, so the sigma portion corresponds to these 3 items, and then this portion corresponds to this portion. So there's a reason why I ordered it in this specific way, but if you want to look at it from the perspective of the bit positions, then -8 plus 4 plus 2 plus 0 makes more sense if you want to align everything by bit position. Alright, so Ashton asks, can you show us that example that you said earlier that would not work with the method used before class ends? Yes. Okay, so the example that we were looking at was 0, 0, 0, 0 minus 1, 0, 0, 0. Okay, so 0, 0, 0, 0 minus 1, 0, 0, 0, and 0, 0, 0, 1, and then 0, 0, 0. And this is going to be a 0, and that's going to be a 1 here, and then we end up with 0, 1, 0, 0, 0 over here. Okay, so this is the one where things do not work out. So I'm repeating what we have already figured out earlier. B is 1, sine is 1, overflow is 1, L is 0 in this case. So we look at this and then we ask, okay, so how come this one does not make sense, right? So we say, okay, 0 only has one interpretation. Okay, it kind of makes sense that 0 is 0, no matter how you look at it. Okay, so we have 0 minus, now 1, 0, 0, 0 has two interpretations. One is -8, the other one is just 8. So let's deal with signed here. So the end result should be an 8. And then for the unsigned case, 8 is representing just 8, right? So 0 minus 8 is supposed to be 8, but with a borrow. Okay. So now we look at this and see if it makes sense in each of these cases. Let's start with the one that's easy first. Okay, let's look at the unsigned interpretation. 0 minus 8 is 8, but it has a borrow. What does that overall borrow means, right? What are we borrowing? We are borrowing from the next digit, which cannot be stored as a part of the difference. So the most significant digit here is representing an 8, which means this one is representing the borrowing of a 16. Okay? So that makes sense, okay? Because I have no money in my pocket. There's a bully outside of the classroom who demands $8. Okay, I go like, I don't want to get beaten up, so I'm going to borrow money from a cop. Okay, I'm going to borrow $16 from a cop, so I can give the bully $8 and leave the cop to do what he needs to do. He or she needs to do. So at the end of the day, I still owe the cop $16. But since I gave $8 out of the 16 to the bully, I only have 8 remaining in my pocket, but I owe the cop $16. So my net worth would still be -8 because I'm actually owing the cop $16 even though I'm holding on to $8 in my hand. I have no idea. Maybe some kind of Northern European country. But remember, the cop gets to handle the case afterwards, even though I still owe the cop $16. All right. So that one works out. Okay, so the unsigned case kind of works out in terms of the semantics. What does not work out is the signed case. Because for the signed case, when you subtract a negative quantity from a non-positive quantity, you should end up with a negative quantity. But I take it back. Sorry, I take it back. When you subtract a negative quantity from a non-positive quantity, you should end up with a positive quantity, which is this one over here. And some of you will look at the number wheel and say, hey, that actually works out too. I don't see a problem in the number wheel, because in the number wheel, 1000, which is the bit pattern that we got as D, is both -8 and 8. But you cannot have it both ways. Okay, if you choose to look at things, if you choose to look at 1000 as -8, you have to be consistent for the entire calculation. In other words, the way you interpret x, y, and d, if you say I'm going to look at these the bit pattern on this side of the wheel as negative values, you have to use that interpretation consistently. So that means if I see it as 0 minus -8, then whatever the bit pattern as is the difference, I have to use the correct interpretation. I have to use a consistent interpretation, which is -8. And in that case, it doesn't make sense. Okay. So I'm not sure whether Ivan is saying it stinks in this case that we have to be consistent in terms of choosing what interpretation to use, or my analogy earlier that I'm borrowing $16 from the cop to pay off the bully who wants $8 from me. So anyway, are we doing okay in this concept? All right. So this is not 8, okay? This is the correct answer. This is the correct answer. But we got -8 instead. So remember earlier I mentioned that this is also related to overflow. So the reason why it's overflowing is because we could not, using the signed interpretation as 4 bits, there's no way to represent 8. That is what overflow is about. Now, I know we are running out of time, but I think it is important to cover this because we have just covered enough material to basically look at what I'm going to present next and make it really make sense, and basically just wrap up everything that we have talked about regarding signedness and regarding the range of numbers. So given n bits, okay, using the unsigned interpretation, the value can range from 0 to 2 to the power of n, the whole thing minus 1. Using the signed interpretation, the lowest value you can represent is -2 to the power of n minus 1. The most positive value you can represent is 2 to the power of -1, the whole thing minus 1. So what this means is after a subtraction, if you choose to look at things from the signed perspective, if the difference is not within this range, then an overflow has occurred. All right, so let me say that one more time. If you look at the minuend and the subtrahend as signed values, now with those two, we don't have to worry about overflowing because we know that x and y has to fall within the range that we are talking about here. But if the actual value of the difference is outside of this range, that means we do not have enough bits to represent the difference, and in that case, it is an overflow situation. So overflow means when we look at things from the signed perspective and we do not have enough digits, basically the range of signed interpretation is not enough to contain the actual difference, then it is an overflow. All right. So I'll give you one more example and then I'm done with this discussion. Okay. So when n equals to 4, then in the sign interpretation, we can range from -8 to +7. So anytime you have a subtraction where the result is more negative than -8 or more positive than 7, then we have an overflow. So I'll give you 2 examples where that can happen. So the first one is what we just saw. Okay, 0 minus 8, 0 minus 8 is supposed to be positive 8. But when you look at the range, positive 8 is outside of their range. So that's one way to get, to basically say, oh, we cannot do this. On the other hand, if you have negative 8 minus 1, which is easy to do, it is just negative 9, but negative 9 is also outside of this range. So both of these would have the overflow flag ending up as a 1. Now I'm going to leave it up to you guys to basically, the first one is worked out already. You can work out the second one where you basically use 1, 0, 0, 0 as the minuend, and then you use 0, 0, 0, 1 as the subtrahend. And you will find that the overflow flag would end up as a 1. All right, so I am done with the lecture today, and the lab is going to be released. So let me go ahead and release the lab for today. So once again, the lab of today is about exponents. So it is related as, in terms of as a primer to what we are going to talk about. And it is already released. You just need the passcode. So the passcode is double. So double here is the passcode to the lab of today. And you have until 1:20 p.m. to finish the entire thing. It basically is a review of math stuff. Okay, it's a review of math stuff that you will need in order to understand the floating point representation that we will get into next Thursday. It's next Thursday because next Tuesday I'm going to talk about the practice exam. One of the questions has been given to you already, and for that specific question, you now should be able to figure out all of the question marks. Now, it might take you some time, okay, to figure out all the question marks, and you might need to kind of use a mentality of solving a puzzle, okay, using the rules that we have talked about in this case, in this class, to help you form the constraints, and then using the constraints, you can lock down the zeros and ones in that practice example. The practice exam is in the text channel from yesterday, I believe. But I can give you the whole exam if that's going to help. So I'm going to use the announcement to send you the entire practice exam. So that will give you guys a little bit more example problems to try to solve. And through that process, I hope that will kind of make you relate the concepts that we have been talking about in this class. Okay, so there's a question of, Professor, is there a resource we could practice these concepts more? I was trying to look up online examples but couldn't find anything concrete. So can Mari Dula explain what concepts are we talking about? Are we talking about concepts of borrowing, binary subtraction, the sign flag, and stuff like that? Okay, so let me send a sample test, okay? Because I think in the lab on Tuesday, I only gave you one example, only one of the questions. So I'm going to send you, using the announcement of Canvas, the entire thing. So give me a second here. I'm going to send that to you guys. This is the whole thing. And let me attach that. Alright, so it's an HTML file. You just need to open it with your browser, and you should be able to see the entire exam. So there you have it. I just sent you guys the entire exam for practice purposes next Tuesday. As a clue, okay, you'll start with the last question first. The first question is the first, I think, two questions are the most difficult, and then the next three are less difficult, but the last four questions I think are the easiest. In other words, there are more determined zeros and ones from the from the bottom up. So if you want to kind of gradually increase the difficulty, work on those problems backwards. Okay, so start with the last one and then move your way to the first one. On the other hand, for those of you who want to kind of really have a good challenge, then you can start with the first one and see whether you can figure it out. If you spend a lot of time and you still cannot figure it out, then you might want to move to the kind of the last one and then work your way back up again, because just getting stuck is not going to be helpful. Now, on next Tuesday, I will tell you how to solve the entire thing. Okay, so I will give you the techniques to do it, and you will realize that you already know everything that you need to know. The question is, can you apply what you have learned combined with problem solving skills in order to resolve all of the unknown bits? Look at this as a Sherlock Holmes mystery. Okay, you're at a crime scene, there are evidence of certain kinds. You understand the subject matter already. You understand ballistics, you understand blood, you understand all the other stuff. So you have all the facts, you have all the knowledge. But the question is, can you infer things, okay, given the evidence, and rule out possibilities and so on? So it's Sudoku, okay? It is basically Sudoku, but using binary subtraction as the set of rules instead of using the usual addition and multiplication as rules. All right, so I'm not seeing any additional questions. I got a few, direct messages that I need to get back to. Other than that, it seems like it's a good time to stop the lecture.